Okay, we know what a relational model is. We know what a database is. We know what a relational model is. We now know what SQL is and what it can do. We're now moving on to the process of designing and building databases. We know what they are. How do we make them? So this is the first section of two lectures on design that we're having this semester. Next week we'll move on to what's called physical design. We're doing conceptual and logical design first. So first of all, a few definitions. So I just was noticing in the introduction that I didn't have a slide that said what the lecture contents was going to be, but basically we're going to talk about sort of what is design and modelling and how they relate to each other. Then we'll talk about conceptual modelling, which is the start of the modelling process, the logical design process, which is a sort of intermediate stage, and that's basically what the lecture's about. Okay, so a data model. A data model, we should know now, hopefully, is a structure for organising a set of data and their relations. So we've got the relational data model, the hierarchical data model, the NoSQL data models, key value pairs, blah, blah, blah. It's just a structure that's designed for storing data and the relationships between them. And there's lots of different ones of them. You can also think about GIS data models with layers and things like that. That's another form of data model. Data modeling is the process of identifying, defining data elements and their relationships. What are the items of data and how do they relate to each other? How do we then organise them within our data model? What data model should we choose and how should we arrange them within the data model that we've selected? Data modelling, and particularly we're talking about database data modelling as opposed to other types of data modelling. And we'll talk about the word modelling as well in a minute, because modelling is one of those words that has 1.5 million meanings. Right, data modelling is one part of systems design, which is the process of defining the components, architecture, interfaces and data for a system to satisfy user requirements. So it's one part of the overall process of system development. And systems design, well, that's what the next line says. The next line says, yes, it's part of the overall systems development process, which is the process of building and maintaining a system. So this is your classic, what's called the waterfall systems development model. So when we started building computer systems, people decided that they needed formal systems and approaches for developing computer systems. And Bennington, the original waterfall model originates in the mid-50s with a guy called Bennington who worked or knew about manufacturing workflow models. So workflow models that have been used in manufacturing processes. It's a linear process. It starts at the start of the conveyor belt. Person A sticks bolt A on bit B, etc., etc. So he took that, the workflow models that are used in manufacturing industry and applied them for computer development. And this is a basic example of the waterfall model. There are many different versions of the waterfall model, but this is my version of it. So you have a number of phases. It's a linear model. You start at the beginning and you end at the end. You start by deciding you want to develop a computer system. You start by deciding what you want your computer system to do, the requirements, identifying requirements. Then you decide whether it's feasible. Do we have the resources to do it? Is it possible to do given available technology, things like that? Once you've decided it's possible and worthwhile doing, you then go into the design stage in which you decide how you're going to build it. This is where the data modelling goes on. What components, how are you going to build this system? What components are you going to build it out of? How are you going to fit those components together? You then actually go away and build the thing. Then you test it to make sure it actually does what you hope it does and it meets the user requirements. And testing is very important because it's notorious for computer developers to decide that users want to do a certain thing, but the reality is users want to do something else. Often users don't actually know what they want. They kind of have an idea what they want to do, but they never, sometimes they're not, until they actually experience something, they don't realize what they really want. Such is life. Implementation, you then roll it out to your users to be in production. You have to run it, you have to maintain it, and then at some point later on you maybe review it. How well is it working? Are there additions that we need to do? Do we need to change it? How successful has it been? So it's a very simple so this is your systems development model for a whole piece of software. And part of that is this design process, and we're going to concentrate on that now. So data modeling is part of the design. It's taking the data and deciding how are we going to arrange the data and what database model are we going to store it in, etc., etc. But we start off by saying, well, why do we bother? You know, why don't we just get to it and build it? What's all this faffing around with planning? You know, let's just get in there and start coding. Well, in many software development models now have much more of that kind of approach, the agile models and things like that, which we'll meet later and probably next term. But here's a report from called the Organizational Aspects of Information Tech by the Organizational Aspects of Information Technology Special Interest Group. It's some kind of government report thing. I don't know who they are. It dates from 1996, but that doesn't change any of these things. So they did a survey, big survey, about the failure of IT projects or success and failure of IT projects, and they identified that 80 to 90% of software solutions do not meet the performance goals, 80% delivered late or over budget, 40% fail or abandoned, less than 25% fully integrate business and technology objectives. Not a good scorecard, not exactly doing very successfully. And you may be familiar with things like this from the news. This is, okay, it's a few years old now, 2013, but these things keep appearing. You'll get a couple of these a year. Abandoned NHS IT system has cost £10 billion so far. So this is a large amount of money potentially involved in developing these systems. So why do things go wrong? So the report not only tried to find out what the state was, how successful we are, but what the problems. And three things that were identified. Insufficient requirement specification. So not actually knowing, deciding what you wanted in the first place. Lack of appropriate design methodology. So things being done in an ad hoc manner and not being done in a structured way. Basically expecting to be able to throw a few people, a bit of data and some software in a room and come up with a solution. So lack of appropriate design methodology. What happens when things go wrong? What are your deliverables? When are they deliverable by? And the poor decomposition of design into manageable components. So the process of the design process, taking apart the problem into its various subcomponents to come up with a decent design. So these things are particularly relevant to data modeling. So these are why things don't go right. Taking it on the other side, if we adopt a formal approach, design a process, what does it do for us? What benefits does it have? Well, we've got 7 there. Prioritize, identify and prioritize user needs. Help the team understand the data and its complexity, particularly relevant to avoiding data duplication, redundancy. You never know your data till you've had your hands in it for a long time, in my experience. I still learn about data sets that I personally collected and have had in my possession for 15 years or so. There's still interesting stuff in there that I've never seen before or noticed before. So finding the gaps in the data, understanding your data. Documenting the system design. We're living increasingly in a world of large staff turnovers, rapid staff turnovers, especially in things like the IT industry, academia, other places. There's always quite often more money around the corner. So we're getting staff loss, staff turnover. Also, our memories are not perfect by any means. I write some code today, I think, oh, I know why I did that and how I did that in 3 weeks' time. And the answer is no, I've moved on, my brain's moved on to something else that's fallen out the back of my head. So we forget, and there's always new people, new users on board who need to get up to speed. So it not only documents things, but we can also help communicate things. Functionality, design, data relationships to the people, the managers, who often have no technical background or limited technical background. So you have to make what you're doing understandable and accessible to not only the technical people, but the managers and the people who are going to actually use the system, who may be basically clerks or something like that. Because you've got everything organized, you can hopefully estimate the time and cost of development. Systems are constant development costs and times constantly overrun. I can't remember where this came from, but you know, I probably invented it now. I've forgotten so long ago. My theory is you lick your fingers, you stick it up in the air, you estimate how long it's going to take, then you multiply by 5, and you're still probably being over-optimistic. So be cautious, be very cautious about how long things take to create and develop. And it provides overall an opportunity to review business processes. So that's why we design processes, development processes and design methodologies are important. Basically, the idea is it helps us prevent us wasting resources and building things that don't work and don't meet requirements. Design. In the literature, there are 3 basically divisions or levels of design. I'm going to be talking here, I mean, some of this is general design theory and ideas, but it's tailored to be specific to relational databases in this case. Later on in the module, we'll be talking about design of programs, web interfaces, and programs that do things. Here we're talking within the database context. We can start off with the conceptual level, in which we design a conceptual model. And that is basically an executive summary of the entire enterprise that you're trying to create. It's an overview. It's an executive picture. What is this thing, this grand thing that we have come here to create? Next, is the logical model. Now we're going to talk about logical. This is mostly about logical models, this lecture. So what a logical model is fully specified, and I should have that in inverted commas because I think that's a wish rather than a reality. Model independent of technology. So it's basically how the system would operate. It's like making a paper version. I think it's like it's coming up with the system on paper, and then when you finally implement that system, that model is implemented in a specific software solution, which is the physical model. So basically, conceptual model, the idea of what you want to do. The logical model, how the system would work in theory, theoretically. The physical model, the reality, the thing that's actually been built and how it runs in a piece of software. Where do these modeling levels match onto our waterfall development model? Well, the conceptual model comes with the requirements. The feasibility basically starts with the requirements, but it's used all the way through the system, really. I mean, I don't know why I've got it stopping at design. The conceptual model goes right back to here, because when you get to the review stage, you look back at what you've built and then look at the conceptual model, and you say, well, have we actually built what the conceptual model originally said or not? The logical model is mostly in the design phase. The physical model, roughly the design construction phase. So basically, these are sort of sequentially done, but they're referred to throughout other parts of the development process as well. Big table. Okay, look at this in your own leisure. But the summary is, so this is a summary table. I really like it. I think it's really useful, actually, to distinguish between what a conceptual, a logical, and a physical model is. So they define different things. The conceptual model, the scope, audience and context of the system. The logical model, the key business concepts and system entities. The physical model, the core data relationships and business logic at a detailed level. Okay, it's not exactly the friendliest language, of course, but basically large overview, getting more and more detailed, more and more specific as we go to the right. Conceptual models meant to be accessible to everybody. Logical models is about communicating between users and managers and the hired IT side who are actually building it. The physical model is particularly of use for the IT specialists who are actually building and constructing the system. So I'll allow you to have a look through. You can look through that table in your own leisure. This is a diagrammatic version of the similar sort of stage, the difference between the conceptual, the logical and the physical model, both as presented as a table and also as a sort of diagrammatic here. So at the conceptual model, we're talking about the different types of entities and the relationships between different entities. We'll talk about what entities are in a bit. Logical gets into more detail. And then the physical, when you get into the physical side, we get into the really small detail and we actually throw away some of the more generalized ideas. So if you can take this as a diagram, the conceptual model just basically has the names of the main things that you're interested here: time, product, sales, store. Logical model, we start to enter in the actual fields that we want to include in these tables. And finally, the physical model, we've actually got the individual data types that we're going to implement in a particular database system, be it Postgres or something like that. So we're building up from a simple sort of framework. We're filling in more and more details as we go from the conceptual to the physical model. Mind you, this is not to me much of a conceptual model. This is a conceptual model drawn by somebody who builds databases, as opposed to a conceptual model built by somebody who's interested in user needs and requirements. Okay. Those two diagrams probably mean very little to you now. But when you've done the logical and physical model, you can go back to those diagrams and have a look at them and those tables and see how those classifications of those different modeling levels differ. So I stuck this in just because it's one of these little asides that I'm interested in and what I find interesting. The whole concept of what a model means, the word model. The word model is used in many, many different contexts. So I think it's useful to actually look at what modeling means, or what the word model means. And this is a very short section to do that. So this is Wartowski, who is a philosopher. I'm not quite sure where he's based, but he wrote the initial chapter in a book on models, Boston Studies in Philosophical Science. And in the initial couple of pages, he states that the symptom of the model is the proliferation of strange and unrelated entities which came to be called models. So the first of all thing he says, there's lots of things that are called, different things that are called models. And he says, in every case of being taken as a model involves a restriction with respect to relevant properties. So what he's saying is that there's a whole variety of models, things that we call models out there. What they all have in common is that they're limited versions of reality. They're abstractions, they're reduced versions of reality. And essentially that's what we use to represent, what we use the word model to represent or to mean. An example of a model is a map. A map is a model. Anybody familiar with Sylvian Bruno, Lewis Carroll, writer of Alice in Wonderland and other wonderful stories? He was a mathematician at Oxford University. Hides lots of mathematical and philosophical questions and conundrums into his books, into Alice in Wonderland. I think Alice in Wonderland can be read as an allegory of mathematics in the early 20th century, among other things, if you're so inclined. So he wrote this rather not very well-known book called Sylvian Bruno, and in it he tells the story. I think I have read the book once, but it's just a man is travelling across through a country, and he meets a map maker. And they were talking about the usefulness of a map. Basically, the larger the scale, as in the smaller the area depicted on the map, the more higher the information content. So he says, well, what scale of map do you need to manage the country? So he suggests, about 6 inches to the mile. Okay, so we are talking a long time, imperial measurements ago, but that was the standard UK county series scale for the UK Ordnance Survey maps at the time. 6 inches to the mile. No, it wasn't. I'm talking rubbish there. It wasn't 6 inches. It might have been the county series anyway. Only 6 inches. Very soon we got to 6 yards to the mile. Then we tried 100 yards to the mile. And then came the grandest idea of all. We actually made a map of the country on the scale of 1 mile to 1 mile. Have you used it much? I inquired. And he says it's never been spread out yet. The farmers objected. They said it would cover the whole country and shut out the sunlight. So now we use the country itself as its own map. And I assure you it does nearly as well. But it's the basic idea of there is no point. A map is a model. A map can only be to be useful, must be a subset, a reduction in the representation of the world. We cannot make a map at the same scale of the world. It's just pointless and meaningless and of no benefit whatsoever. So basically every map is a model. It's a selection of subsets of things in the world and how they're displayed. Final thing on models is another great quote, George Edward Pelham Box. Who knows what Mr. Box is most famous for? Box plots? He invented the box plot, the statistical box plot. Go home, that's your homework. Go and have a look and find out what a box plot is if you don't know what a box plot is. He invented the box plot, and his famous quote, which I love, is all models are wrong, some are useful. So every model is always wrong. It's not an accurate representation of reality, but whether a model is any good is context dependent. What you're going to do with it, who you are. So models come in many shapes, many sizes, many styles, but they're all abstractions of reality. They're all simplifications of it. So we can have physical models like this flume, river flume, chamber, sand, gravel, run water down it, model how rivers flow through that text. We can develop things like conceptual models. This one, the water cycle. Data models, GIS data model. Statistical models, linear regression. Simulation models, climate simulation. They're all simplifications of the world. Conceptual models. Okay, I'll come back from our brief trip into what is a model. Conceptual model. So what is a conceptual model? So we start off in our design with a conceptual model. So a conceptual model is an abstraction of the world designed to facilitate understanding of the concepts, entities, and relationships within a system. A mouthful, but basically an overview or an executive summary of a system. Process function orientated often. Stimulate discussion. Show what you're trying to do, proposing, and stimulate discussion. Well, we've seen this one already. This is a conceptual model of the water cycle. What are the various objects? Infiltration, freshwater storage, lakes, evapotranspiration. We've got various processes shown by arrows, physical features. So we've got objects, we've got flows, we've got processes. We can get an overview of the relationship between water on the land, in water bodies, and in the atmosphere. Nice overview. Here's a conceptual model from a scientific paper, the Journal of Biogeography, and its attempt to show how patches vary at different spatial scales. So we've got local scales with buildings, fields, orchards, landscape scales, individual settlements, regional scales with occupied areas, and continental scales involving cultural regions. So it's a conceptual model of how land use patches, the objects and entities of landscape patches vary with spatial scale. Here's another type of conceptual map. This is an example of a mind map or a concept map, which I imagine most of you are pretty familiar with. Boxes and lines basically connecting ideas to create a structured overview of a topic matter. So this is actually a concept map of what concept maps are. So it's a meta-concept map, possibly. So a concept map represents organized knowledge needed to answer a question, includes feelings, effects, comprised of concepts, using linked words, propositions, etc., etc. So here's an actual example of one drawn by, I think this is a sort of school project, but it could easily be an undergraduate university project. A mind map of population on the planet, impact, various things like impacts, loss of biodiversity, related things coming out from these various spokes from the centre like that. So that's an example, another example of a conceptual model. They don't have to be, they can be anything you like. I like this one, the cultural iceberg. It's about culture, which I know, can't say I'm an expert on culture, but we've got surface culture, the things that we see out there in the world as we wander around, food, flags, festivals, performances, dances, arts and crafts, etc. The physical things that exist in the world. And then down here we've got the things that produce, the underlying things that produce these physical artifacts on the surface. So we've got things like notions of courtesy and manners, friendship, leadership, personal space, cultural things about touching, tones of voice, displaying emotion, all these things that together help create or underlie these physical artifacts in the world. Here's another one. This is a concept model for the Gulf of Mexico. Integrated science, so we've got information and people interested in ecosystem structure and function, geology, geomorphology, sediments and things. And then we've got the various topics covered by these different areas. And then obviously they're trying to build predictive models for the Gulf of Mexico estuary, which requires the integration of all these data from information and concepts from different disciplines. Okay, concept models. So let's get a bit more IT rather than sort of general concepts. So here's an example of a conceptual model of the Flickr photo sharing service. Flickr being one of these places you can upload photos to. And so this is drawn by Bryce Glass. So we've got users, we've got photographs, we've got the subject matter of the photographs, we've got content, the things in the photographs, people, actions, objects, places. We've got sets of photographs, we've got the tags, we've got groups of people who are collecting photographs on single things. So for the Flickr community and the Flickr IT system, this is providing us a conceptual overview of the people, technologies, and culture of the Flickr photo environment. Let's get a bit GIS-y. Just when I was looking for conceptual models of GIS, it's surprisingly hard to find them, actually. I'm sure they exist all over the place in reports and things like that, particularly from things like consultancies and computer software development companies. But actually searching for them on Google on the internet is actually quite hard, so I didn't actually turn up many really good ones. Anyway, this is one that I did turn up. This is the Soccer World Championships in Germany 2006, and it's a conceptual model of the location-based services set up during the football tournament. So we've got things like controls of signs and guidance. I've no idea what pseudolights is. Anybody got any idea what pseudolights is? No idea. Anyway, it's to do with data exchange, setting up the wide area network. We've got Bluetooth communications that are going to things like service providers, basic information, mobile communication systems. It's all to do with communications and stuff like that, but that's one example of a sort of conceptual model. Even if we don't understand what it actually is about, we can see that it's to do with how the various technologies are used to exchange data between the various organisations involved and places involved in the championship. Here's a classic one from Esri. This is probably the one that you see more often than anywhere else as your classic GIS enterprise design from the Rhode Island Department of Transport. So we've got various, in this case, various departments and things like that, and how they link together, how the GIS services link together. So we've got public web applications, we've got Capitol Hill, so this is the central administrative area. We've got the health infrastructure area, various other bits. So that's your conceptual models. Basically, draw a picture of some kind that shows, illustrates, provides an overview of what you want to do or what you are doing. Make it accessible, don't make it too detailed. So if we go back to that table, so one of the things that it says is a conceptual model probably shouldn't have more than 20 or so objects depicted on it. You know, keep it simple, keep the language simple, avoid technical language, make it accessible, make it interesting, possibly. Okay, so we've drawn our diagram for what we want. And as I say, if you find some conceptual models of GIS that you think are better than those ones, then send them in, because I'd like them. So we then move on. We've got our idea. Let's assume that it's feasible, etc., and we're going to do it. So the next stage in our modelling section is to move on to the logical model. Now, I have put it in inverted commas here, a fully specified abstract representation of a system design that is independent of any particular software system. So you're making a design, but one that could be applied. So if it's a relational design, it could be then implemented in MySQL, Oracle, Access, any relational database management system. We do the physical model next week, but it's useful to see what a physical model is now, because I will talk a little bit about it. The physical model is the logical model implemented in a specific software. Already mentioned that. Okay, so this diagram showing the whole sort of process, conceptual to logical to physical. We start with ideas, we're ending with products. And in the in between, we have to design and build various things. We have to build our system. So we need a hardware architecture. And architecture is just the components and how they fit together to make our system. So we need a hardware system, a hardware design. We need software design that runs on that hardware. We need an interface design that allows the user to interact with the system. These are mostly covered next after Christmas. Here we're concentrating on the data modeling component, which is turning your ideas into either a relational database or possibly an object database. This is the path we're going to travel from our ideas. We're going to do entity relationship modeling to identify, that's how a logical modeling process, that's what the rest of the lecture is about, which allows us to produce our tables in our relational database system. If we're going an object approach, we would use an alternative logical modeling approach, almost certainly what's called unified modeling language, which is an object-orientated approach, which will give us an object-oriented design at the end of the day. Again, getting pictures of logical designs is problematic. And I think this is a good example of where the whole, let's say, how people use logical, conceptual, separate logical and the conceptual is perhaps different. People use it in different ways. So this is figure 5, Geographical Information System Logical Architecture, from a paper in Future Internet in 2012. GIS module. To me, that's a conceptual design, perhaps, probably. I think the take-home message is, these diagrams, you can call it, there's obviously some things are clearly conceptual designs, some things are clearly kind of logical designs, and then there's stuff that kind of has a bit of both, an element of both in. Or maybe people have just misnamed it, and we should perhaps the reviewers should have said, hold on, that's a conceptual design, not a logical design. I would certainly call that more of a conceptual design than a logical design anyway. So, all right, we've got another 10 minutes. Entity relationship modeling. This is a logical design approach technique for turning your ideas and the information that you have into a relational database model. This is the most important component probably of your database modeling, data modeling problem. And it's a graphic approach to specifying the logical design of a relational model, originally published by Chen in 1976. These graphics represent the entities of the system, their attributes, and the relationships between them. It's a software-independent approach. After all, this is a logical modeling approach, so it has to be software-independent. Drawing of ER diagrams facilitates the understanding of the domain. The very process of drawing the diagram is an integral part of understanding and developing your understanding of a system and the data that lies within it, or the data that you're going to contain within it. Beware there are various notations, there's not one single notation, and there are often different ways of representing the same model. So one ER diagram, two ER diagrams could represent the same, overall same model. These are what they look like. That's an example of a one. I have no idea what creep is. I have no idea what a character, region, item. Looks like something to do with a game, some sort of fantasy game thing or something. Doesn't matter. That's just to give you a picture of what overall of what one looks like. So let's go inside that and see what those components are. So the first thing we need to know is about entities. It's about modeling entities, attributes, and their relationships. So what is an entity? Again, we've got this problem of people using different words to mean the same things. So an entity can be used to describe a specific real-world object, concept, or event. So example, my dog Rover, not that I own a dog called Rover, but it's a dog, it's a real dog, and its name's Rover. And that is sometimes called an entity, but I tend to call it an instance. And I think most people use instance. And then the other thing we're interested in is which is also called an entity, and it's what I use the word entity generally to mean, or it's also sometimes called an entity set, which is a collection of instances of an entity that share a common set of attributes. So dog. All dogs have a name, they have a colour, they have a whatever else dogs have, tails, I don't know, bowls, chew bones. So basically, this is the class dog. This is the specific instances of dog. And just bear in mind that sometimes the word entity will be used to represent an individual instance, and sometimes it will be used to the class. I tend to use it for the class, I use instance for the individual instance. So what kind of entities exist? Well, it depends on the system that you're interested in. So in a university system, we might identify students, faculty members, courses, etc., etc. Airlines might be interested in aircraft routes, neighbourhoods, roads, properties, etc. And then each of those entities has a set of attributes, things that describe them or are needed to describe them that go with them. So within the university, one of the entities is a student. A student may have a student number, a name, a date of enrolment. An airline, one of the entities of an airline is an aircraft. An aircraft may have an aircraft number, a sum of how many hours it's flown for its maintenance record, things like that. So entities have attributes. On the entity relational diagram, this is how entities and their attributes are often represented. This was the original Chen notation. So entities are drawn in rectangles. Attributes are drawn in ovals, named in ovals, connected by connecting lines. So the student here has 5 attributes. The student ID is the primary key. So the convention is to underline the primary key. Primary key is the unique identifier for that entity. Then we've got two normal fields, surname, forename. Notice there's nothing about text, nothing about numbers, so we don't care what data type it is, it's just got the name of it. And then we've got another one here called overall grade. So we want to know what the overall grade of that student is at the end of their degree. Overall grade is not something that you enter into the database as a number. What it is calculated from all the results throughout your modules and your courses. And calculated fields are given this dashed or dotted outline. So they're calculated from other information. Fields may also have multiple values here. So this is not the same as a database. This is the difference between a database field and an entity field or attribute. So for example, nationality. Students have nationalities, but some, I don't know any of you, have dual nationalities. So some of you may actually have multiple nationalities, citizens of multiple nations, in which case we can use the double circle to represent the fact there might be more than one value associated with it. Relationships. Relationships, so that is entities and their attributes. It's as simple as that. Relationships are associations between entities. Important, it's between entities, it's not between attributes, it's between entities. So here's a really simple one. A person owns a property. One entity person, one entity property. Person owns the property, that's the relationship. A property could be within a neighbourhood. Every house is within a neighbourhood. And here, this is an example drawn as an entity relationship diagram. We have a house entity, and it has a postcode, if a postcode is an entity. Whether a postcode should be an entity is another question entirely. But in this case, it's been designated as an entity, and a house has a postcode. You might wonder, well, why were you doing that? Well, in fact, obviously, there are many houses in each postcode, and a house, depending what a house is, if it's a large block of flats or something, it might have more than one postcode even, I think. So, entities can have more than one relationship between them. So, here we've got a road entity. Oh, that's not a road. Oh, yeah, well, sorry, that should be town. That's incorrect. The one on the right should be town. Or city. Sorry about that, that's an error. So a road starts at a town, city, ends at a town, a city. Chances are the road is going to be a different town and city at the start and the end, but you never know. It could be a little loop road or something like that. So you can have multiple relationships. Really just a couple of minutes more. Relationship attributes. Relationships themselves may have attributes. So, footballs or competitions. There's teams. Teams play a match at a location. The location has an address and a name. The match has a score. So it's the score is an attribute of the relationship. So relationships can have attributes. You may have also noticed in that diagram there is this double connection between team and visitor, a match. Well, there's two teams in a match. There's a visiting team, home team, and an away team. And that's an example of what's called a recursive relationship, a relationship between an entity and itself. So it's a relationship between one or more instances of an entity. And that requires the roles, these are the roles, to be defined. So here's another example. We're an employee, I'm an employee, Andy Swan, my line manager, head of department, is also an employee of the university. I am the worker. He is the manager in that relationship. Let's stop there. Okay, so we'll reconvene 10 minutes up in the lab, finish off this as quickly as possible, 20 minutes, and get on with the ER exercise. All right, we'll deal with any questions.